So, as you heard from Stephen, MWA project is making this transition from phase 2 to phase 3. So PFT science, which was traditionally associated with the VCS capability, is also in an interesting situation. So the chapter 1, which was like using VCS for a lot of pulsars and transients, what we can do is almost coming to an end. And chapter 2, which is like a beamformer era, which has not begun yet. So we are somewhere in between that chapter 1 and chapter 2, but it's not a blank page. We are still doing a lot of good science. And just a quick reflection, the 10 years of VCS has been a great opportunity. It helped us to learn about the system and give access to unprocessed data to many of our students and ECRs, and close to 50 publications, 10 PhD completions, and a lot of good work. And I should also say that a project like a SMART would not have been possible without VCS capability. So in retrospect, it was really like a great move to go for. Okay, so I'm just going to give you like a little bit of a quick overview of what we have been up to over the past year, and then we'll give you a couple of quick comments on what sort of science we are thinking in the next several years. So you all heard about this SMART survey. Christian nicely introduced it yesterday. It's our flagship project, quite an ambitious survey, all Southern Sky Highway for pulsars and fast transients. And you will hear from Chiamin in a short while. And I just wanted to tell you that the whole data collection is complete. And yesterday, Stefan mentioned that they couldn't do like a South Celestial Pole in Gleam or GleamX, but we have been able to do it because Stephen, with his discretionary powers, approved that observation for us. And so, like any other observation, we should be doing like complete quality checks. And this is that nice detection of the crab pulsar from South Celestial Pole observation. And we know MWA can do such wonders. And this is that nice beam map. So you are pointing to South Pole, but you can crab is like happily there in one of the grating lobes, which is as powerful as like your main lobe. But the intent of doing South Pole observation is obviously to get a pretty decent sensitivity in that part of the sky. And the closest pulsar you can get is about something like a -75 detectable pulsar, but you can still detect it with a few minutes of observations, even though it is on the beam edge. So we are pretty happy with the data that we have collected, and it's all in the CAN, 4 petabytes, and nicely calibrated and quality checked. So you are going to hear all about the nitty-gritty of a second pass processing from a Chiamin, so-called second pass. If you don't know what first pass is, it was just a shallow survey for a small patch of the sky, and that discovered like half a dozen pulsars, and all shown in like this gold and yellow, and so-called first pass discoveries. And again, quite a few 3 PhD completions, and several papers all came out of it. Second pass processing is what is really has been keeping us busy over the last year, and I will let details to Chiamin. All I wanted to mention here is that even after processing like a small fraction of the data, we have already increased the number of new pulsar count by more than 3-fold. So pulsars are trickling out, and our current focus is going to be like a Southern Cap survey. That's the reason why we didn't want a hole in the Southern Cap. That's the reason why, motivation to complete that particular observation. So once we find a pulsar, because our beam size is 20-24 arc minutes, we need to get a better position so that we can follow them up using a phase 3 MWA or Parkes or any other telescopes. So Bradley and Arash has developed this very nice algorithm that takes advantage of the fact that we understand our beam pattern, we can simulate it, we can go back to the voltage data and regrid the positions to our Hartz content and go from that 20 arc minutes to something like a 1 arc minute, 2 arc minute position so that we can go to the other telescopes. And that paper is now very close to being accepted, and you can soon read that on arXiv. So finding new pulsars and doing science is one big thing. That's the primary thing we want to do, but that's not the only thing that we have done this SMART survey for. It's an excellent digital record of the entire southern sky in very high time resolution and very long dwell time. So one of the ideas was to build up this complete catalog of low frequency pulsar detections. This is incredibly important, especially now with the SKLO constructions ramping up. So 2 years ago, when we published the first 2 in the SMART series, we had this 180 pulsar detections. Many of them were made at the first time at low frequencies. 2/3 of them were made using the SMART data set, the kind of data set we had access to now. And thanks to all the hard work that has gone from Chris and many others. We have now increased that sample quite substantially, more than 250 pulsars, and including 40 millisecond pulsars. So you will hear from Chris more about it. But I just wanted to mention that our intention is basically to make all useful data products, including full resolution, multi-channel profiles and archives and all the measurements publicly accessible. And part one of that has already happened. That is Chris's paper. Part 1 is 2 is at works, and it should be with the journal, hopefully within the next couple of months. I simply cannot resist showing this very nice plot that Chris gave me 2 days ago, which is rotation measurements, very precision measurements of a good sample of pulsars. It's nicely matching my mental picture. Many of them are actually away from the plane, and that is where you don't have like a very precise rotation measurements, at least from pulsars. And this is even nicer plot, that smart RMs are compared against the PSR CAT RMs for a subset of pulsars. And you can see that is such a beautiful match. And so we are at least to first order getting everything right. Garvit, Garvit is not here for some very important reason. You heard from Sylvia. She is counting days to her submission. And so it's with Ash, who was presenting today. Garvit is in fact counting hours. So if you see Garvit tomorrow at this time with a happy smiling face like that, that means he has submitted. Okay, so this is the second last chapter of his thesis. So the theme was basically look at the long period annulling pulsars and their proximity to death lines, so-called death lines, and that is where the pulsars stop emitting. And he was looking at this, I think something didn't show up there, so don't worry. So he developed a new algorithm that basically uses like a sums of the pulsars, a technique that can be more robust even when observations are limited by signal to noise. And an earlier work showed that a subsample of those pulsars are sitting in the death valley. As you increase the sample, pulsars are not letting you converge on some interesting conclusions. And same thing is happening with linking pulsar emission properties to properties like a spin down luminosity. Again, that paper is very close to being accepted, so you will soon have it in the archive and you can read all about it. Sammy discovered this very nice pulsars. It was originally discovered in the GleamX using the transient pipeline that Natasha mentioned yesterday. But we have this excellent resource of smart data sets. So we were able to confirm it using smart data and do a lot of great work. Turns out to be a sporadic emitter, more like in the nulling kind of a category, but more like an RRAT, which stands for rotating radio transients. Again, Sammy's paper is published, and so you can go and read all those details. And VCS has also been used for like a triggering on transients like a GRBs. And again, I showed this work last time, but the big difference is that now the work is published. So at least on 2 GRBs, they were able to get this curious 6 sigma, 7 sigma kind of a signal, which turns out to be like a signal from a digital TV and nothing that requires you to jump up from the chair. But again, it shows nicely that demonstrates the kind of capability that MWA has. Okay, so a couple of quick words about the papers that are led by our external collaborators. Jonah Rankin, who is an exponent in the field and has been working on this field from the day one of the pulsar, an expert in pulsar emission, beams, and so this is the work that has been done that combines the smart data and along with like a lot of other data from different telescopes, all the way from UTR2, which is observed at 11 megahertz, unfortunately destroyed by the invasion of Russian Federation Army and recently, but the data is still there. And the 5 gigahertz data point comes from Arecibo, again, unfortunately collapsed, but all the combination of data is giving us like some very interesting results about the pulsar emission heights. And it's all estimated using special relativistic aberration and retardation effects, which are the solid physical basis. The most important result here is that, as you can see, this emission heights, regardless of the frequency, all the way from 10 megahertz to 5 gigahertz, it's all around the 200 to 300 kilometers, which is quite a shocker in pulsar astronomy. The reason why you can do this for these pulsars, because it has this beautiful profile, which can be modeled as like a core plus double cone kind of a profile. And Jonah Rankin has another project and working on a similar analysis on another interesting pulsar. And this is borne out by multiple different targets. That will be quite an interesting result and for pulsar astronomy. Jim Cordes, and who is a world-leading expert in pulsars and ISM, has been interested in low-frequency measurements and profiles coming out of MWA. This is some work that Jim and Abra have been doing. Abrice is one of his undergraduate students, on looking at the pulse broadening, which is essentially like a multipath propagation effect, and the smart data in combined with data from their own project, and has been used to look at the frequency dependence of the pulse broadening. So before this particular work was done, and this particular line of sight was deemed to be like a pretty anomalous. But once you put in all the new measurements, it looks like it's all like a nice and clean and happily matching with Kolmogorov. But that's the punchline of this particular paper. This was also a pilot to exploring some very, very subtle effects in interstellar medium that Jim has been working on, which basically suggests that you can have like a frequency dependence or chromaticity of the pulse broadening function due to some interplay between inner scale and the screen geometry. And MWA happens to be at the sweet spot of exploring that and could be like a very nice phase 3 project. VLBI, Shintaro gave me this very nice slide. And as you might remember, ages ago, we established at least I wouldn't say established, saw fringes between GMRT and MWA after quite a strenuous effort, that is 7K plus baseline. And more recently, they did the same thing between IPRT and GMRT. And now we are trying to push that between MWA and IPRT so that you can complete the loop. I'm sure Tasso and Phil will be very happy about this if this goes forward. But again, the bottom line is that, MWA face-up beamformer is basically the key to getting it done. And speaking of the beamformer, and okay, good. 3 minutes are fine to talk about the beamformer because it is the future, right? So beamformer, I don't need to tell you this. It is going to be a game changer for a lot of PFT science. Things which we have been restrained for ages, things which we were not able to do for ages, we will be able to do it in the near future. Like looking at targeted searches, doing monitoring FRBs, at least the active ones, or pushing the MWA to low frequency VLBI and lot and many other projects. The things which I really want to highlight is the things which are really important and must be done kind of a category. One of them is to do with the timing new pulsar discoveries from SMART. Because finding pulsar, discovering it or confirming it, like I have been saying, it's step number 0. Step number 1, 2, 3 is all like going after those pulsars, timing them, regular observations. That is how we get to measure the spin parameters, astrometry, and know more about the pulsars. That's the real science. It's all coming out of that. And we have nicely demonstrated that the Discovery telescope is the best instrument to do that initial phase connection, and using our first discovered smart pulsar. And VCS, even if it was available, it is not a great capability for that because oftentimes we struggle to meet target-specific cadence demands, which requires like observing the same target multiple times a day or week. And as a matter of fact, only 3 out of 18 pulsars we have phase coherent timing solution. So having a beamformer means we are going to greatly accelerate science from the SMART. So that is pretty much critical. So in fact, it is a perfect timing. We just collected all the data, starting to find the pulsars in lots, and we really need like a beamformer. So it is as simple as that. Okay, so another dream project, just like the combination of phase 2 upgrade and the VCS gave us the opportunity to take up something like a smart survey, which is like a legacy project for MWA. The combination of a phase 3 and the beamformer is going to give us like an excellent opportunity to launch a pulsar monitoring project. And a big motivation of that is all coming from like a recent high-profile results coming from pulsar timing arrays, which you all may have heard about. So multiple PTAs reporting like a 2 to 3 sigma kind of a result, very tantalizing, very solid, but very interesting. One of the big things that has coming out of it is that ISM source modeling, ISM noise modeling is incredibly important. This is something that has been nicely demonstrated in the PPTA analysis papers. So it boils down to understanding the local ISM where your IPTA pulsars are in and out in great details. That's what the Daniel Reardon's paper says. So again, MWA is the best instrument for that. And someone asked, Divya asked, Greg, how many beams we can form? To me, going from 0 to 1 is enormous improvement. Obviously, 2 is better than 1, 4 is better than 2, whatever. But the point I want to make here is that MWA is the only telescope that can do this. At the northern hemisphere, you have like a multiple low frequency instruments like GMRT and LOFAR and so on. But there is nothing in the southern hemisphere. But that is where the future of PTAs are going to be. SK Emit, Meerkat++, all of them are going to come there. So it's a great niche science for phase 3, enormously great value for a high profile project, tons of ISM science. And of course, we will publish this data through Swinburne Access Portal so that everybody can access it. And this is all in preparation for SK era. So to sum it up, a decade of productive science and learning with the VCS, and the science extraction from SMART will continue as a priority. And you will hear from Chris, Jiamin, and Chuyang and Piyush all about the great stuff that is happening behind the scene. And the beamformer will bring in like an excellent range of opportunities. Thank you.
A wonderful summary. Thank you, Ramesh. Do we have any questions for Ramesh?
Thanks for waking me up, Ramesh. That was awesome. How long do you need to observe in order to achieve an effective PTA?
Okay, so let me just clarify. I didn't mean like as doing this in competition to PTAs. This is more like a supporting project for PTAs. PTAs needs the data sets from all across the frequencies to do excellent noise modeling. But to be useful as like a data set that PTAs can use quite meaningfully, you are talking about a minimum of something like 5 years. 5 years is the kind of data that Meerkat is still waiting to produce so that they can get into like a international PTA consortium, and because you have to make this data available to them for doing some decent noise modeling. So that's a kind of rough timeline. But I should also clarify, in the name of PTA, we are just proposing a great project for MWA. It's not just that you want to look at only the PTA pulsars. Any pulsars in the, within 3 kiloparsec will be fantastic. Because the goal is here to understand how the ISM is and characterize it in, to your heart's content. So every single pulsar. The nice thing about that, Chris has shown this, in this red ones are all like a pulsars within 3 kiloparsec. And every single pulsar is going to give you a measurement that is useful for modeling the local ISM. Whether it is pulse broadening, scintillation, doesn't matter. And you need to look at it at least at the level of like a PTA cadence, which is once in 2 weeks or once in 3 weeks. Once in 2 weeks is ideal. That's the idea. And we can, that might immediately give you like an alarm bell saying that I'm going to come back with thousands of hours. I might. But if we have like instead of like 1 beam, n beam, could be 8 or 16, that will be like reduced by factor of 16. As you can see, at any spot, if you put a like MWA field, there is happily like about a half a dozen to 10 detectable pulsars in the field. That is one of our big strengths, which no other telescopes can talk about.
Wonderful. Maybe we've got time for one more quick question, Richard.
Yeah, it was a great talk, and it certainly woke us all up. This is a real-time beamformer, isn't it?
Yes, yes.
So you're going to need real-time calibration.
Yes, absolutely, that's correct. Yes, and I think, yesterday, none of the operations teams are here, but if Chris and Greg, that in their presentations yesterday, they said that's exactly the path they are working through. In fact, Bradley, who is sitting just behind you, might be able to say what is that they are doing as part of that OSIS-RC support project to get there.
Okay.
Would you like to?
I'll pass it to him. But
yeah.
I'll just say that we're doing exactly the same thing for the SKA.
Yeah.
SKA-low, and yeah. We really should make sure there's no duplication.
Okay.
Yeah, so the idea is essentially using those Kelvin machines that Greg was talking about that does the calibration solutions essentially whenever one comes off the telescope. We will know in advance when one of these beamforming observations is coming up, so we'll prepare, and that goes to the database, and then you can essentially call that. No, but for the beamforming, you don't need it to be updated necessarily in.
Yeah. For the beamforming that we have been doing with MWA, we can just work with a one single calibration solution for the entire hour.
Yeah. So
6 kilometers at a frequencies 100 megahertz, 140 megahertz. We didn't have an issue. Every single data that we show you are from a single calibration solutions that is before. We can come back to
Let's
that.
continue this discussion offline. But I'm glad that we've inspired some great discussion between the group. So let's thank Ramesh again.
Okay.
We'll now have Chris Lee talking about the millisecond pulsar census. Thank you, Christian. Oh, what is, do you want this? Do you know more? Better. Okay.
Great. So, good afternoon, everyone. So, I talked a little bit about this at last year's MWA meeting, but I'm excited to give you a more complete summary of our census of millisecond pulsars using the MWA. And of course, I'd like to acknowledge my PhD supervisors, Ramesh Bradley and Willem van Straten. So pulsars slow down over time due to the emission of dipole radiation because they're essentially just rotating magnets. And eventually they die, but plenty of pulsars are in binary systems. And those in binary systems, of course, have companions that eventually will evolve and can begin to transfer matter and angular momentum onto the neutron star or the pulsar. And that process is called recycling. And it spins the pulsar up to much shorter periods and also reactivates the pulsar if it was already dead before. And this process also degrades the magnetic field of the neutron star. And basically what we're left over with is a pulsar which is much more stable and much more precise when you're timing it than a regular canonical pulsar. So millisecond pulsars are incredibly useful. We can use timing of the arrival times of their pulses at our telescopes to measure very important parameters like the neutron star mass, the companion mass, and also parameters about the interplanetary and interstellar medium between us and the pulsar. And we can also use these times of arrivals to measure relativistic effects like the decay of the orbit of the pulsar due to the emission of gravitational waves, and also time delays due to the pulses moving in and out of gravitational wells. And actually measuring these effects can help us to test general relativity itself to a precision which in some regimes is actually completely unrivaled by any other methods of measurement. And also measuring the times of arrivals from a network of millisecond pulsars called a pulsar timing array, we can look for correlations in all of those signals to search for what we call the low frequency gravitational wave background, which is theorized to be produced by a superposition of gravitational waves emitted by far away supermassive black hole binary systems. But also the search for these low frequency gravitational waves, there's a lot of hopes for discovering new physics in those signals because obviously we're probing a regime which hasn't been observed before. So observing millisecond pulsars and having precise times of arrivals is incredibly important for achieving these goals. So we currently know of about 550 galactic millisecond pulsars, those being those outside of globular clusters, but less than 10% or around 10% have been detected below 300 megahertz, which is of course the observing band of the SK low. And in this frequency range, a lot of the emission and propagation effects are much more strong, or they're at least frequency dependent, which means that we can measure them more precisely than we can at higher frequencies, which is where wideband low frequency instruments like the MWA come into play, because we can use it to, for example, measure the dispersion measure very accurately over a long period of time and use those measurements to reduce red noise in the signals of timing experiments, for example, like pulsar timing arrays. But the problem is that we don't actually know what MSPs are detectable at these frequencies, and we also don't really know what their emission effects are like if we haven't observed them at these frequencies before. So a catalogue of detections in this frequency band will be useful for planning future surveys, and as also for during commissioning stages of the SKA low, when you want to compare between telescopes. So you've probably already heard about the voltage capture system. So it essentially records voltages from all the tiles, or about 128 tiles in phase 2 of the MWA. This is incredibly flexible data, and for our purposes, we do offline tide array beamforming on GPUs. This outputs 24 coarse channels with a time resolution of 781 nanoseconds, although we can, in the post-processing, trade off between the frequency and time resolutions. And since we output from the beamformer complex voltages, we're able to do phase coherent dedispersion, which lets us essentially recover the very short timescale structure in the pulsar signal, for example, like the pulse profile here. So the goal of my project was to do a census of MSPs in SMART, which obviously covers the whole southern sky in VCS pointings. So I ended up beamforming on about 150 MSPs, which is about half of all of the even potentially detectable MSPs, those being the ones in the declination range of the telescope, and also with a scattering which is less than the spin period, meaning that it's able to be phase resolved by our telescope. And this involved processing about 1.5 petabytes of VCS data throughout 47 of the SMART observations. So before my project, this is how many MSPs we had already detected using the MWA, both through targeted studies and also through the earlier searching. And after my processing, we've increased this number to 40 detections. And you'll note that a lot of these detections are actually along the galactic plane in the orange pointings and in some of the purple pointings, which were the last observations to be collected for the SMART survey. So I actually helped to collect and verify those observations as a part of this project. So those are the ones following the galactic plane, and they were collected with the MWAX VCS system. So 16 of these detections have only ever been detected at low frequencies with the MWA. 11 of them are the first ever at low frequencies. And I put them on a PP dot diagram here, which is, of course, a pulsar astronomer's favorite diagram. The blue points are from the initial census. So this is all redetections from the initial census in 2023. All the red points are all the detections we've made since then, and you can see that we've quite drastically increased the number of MSPs that we have in our sample, and we're sort of spreading out in all directions, probing more of the parameter space. So what can we do with these redetections? Well, we can measure their time average properties, like their pulse profiles and their polarization, and we can also very precisely measure and report their dispersion and Faraday rotation. So here's a gallery of what we call the integrated pulse profiles. So on the x-axis for each of these plots is the rotation phase of the pulsar, the complete rotation phase, and then it's just radio intensity on the y-axis. So you might notice that the pulse profiles are much broader and more complex than regular pulsars. This is a feature of millisecond pulsars. And also, for quite a lot of these, the scattering is quite prominent, and that's because scattering is a lot more noticeable when you're looking at much smaller timescales for the same distance, because of just like the proportion of the scattering timescale and the period of the pulsar itself, which makes it quite difficult to detect millisecond pulsars at these frequencies. So to measure the flux densities, we used a beam simulation method. So we simulated the tide array beam across the whole sky, multiply that with the sky temperature and integrate over the sky. To speed this process up, we only integrate where the primary beam pattern or the primary beam power is greater than some level, 0.1%. That means that we only have to integrate over about 60% of the sky, because outside of that region, it doesn't contribute a lot to the integral. And then we also compute the sensitivity on multiple frequency and time steps, because the pulsar moves through the beam, and the beam changes as a function of frequency as well. So you need to account for that in your sensitivity measurement. So we validated our measurements against LOFAR and Meerkat. So on the left is a direct comparison with LOFAR, common LOFAR detections of LOFAR. And we essentially have pretty consistent measurements within about a factor of 2 of their detections. And then on the right, it's also a direct comparison where the diagonal lines show the spectral index, which is needed to account for the differences in flux density between our measurements and Meerkat. And they're centered about -2, which is pretty standard for millisecond pulsars, which means that this is kind of like an indirect validation of our flux density measurement method. So Faraday rotation is when you have a signal, a polarized signal traveling through a magnetized ionized medium, and it rotates the linear polarization vector as a function of wavelength squared at a rate which is proportional to the rotation measure. And that means that if you have a large fractional bandwidth, then you can measure the RM quite precisely. So we did this for all of our detections using RM synthesis. We then corrected for the ionospheric RM using global models. And we typically have a precision of about 0.1 radians per meter squared. And this is comparable to what's usually reported by PTAs like Meerkat and Parkes. But their measurements are usually averages over several or even tens of observations where they just take the RMS of their measurements. But from a single epoch, we're able to consistently achieve this precision. And we can use these measurements to do, for example, probing the galactic magnetic field, which Ramesh also mentioned. So I also looked at whether the RM is changing across the spin phase of the pulsar. So this can be potentially created by either scattering, profile evolution, or potentially emission effects like generalized Faraday rotation. Obviously, you don't immediately know what is causing that. But for example, this pulsar, 2241, which is a very fast Black Widow pulsar, we detected variations in the RM of the order of about 1 RM unit or 1 radian per meter squared, which we believe are due to scattering, which means that we're essentially detecting scattering for this pulsar on a timescale of about 10 to 20 microseconds, which is incredibly fast just by looking at its polarization. And the last thing that we looked at is profile evolution over frequency. So regular canonical pulsars, they usually evolve quite dramatically over frequency. Specifically, their components will usually drift apart at lower frequencies because you're looking at different parts of the different altitudes of the magnetosphere. But since millisecond pulsars are spinning much faster, their magnetospheres are much more compact, and the emission that we observe over large frequency ranges is coming from a much smaller altitude range, which means that the spacing between the components as a function of frequency barely changes at all. But what happens is that the relative amplitudes in those components changes quite dramatically, and that can be due to a number of effects, including like aberration and retardation, which is something that Ramesh also mentioned in his talk. So we've seen some quite dramatic changes compared to the Meerkat detections. And then we also noticed that a lot of our detections are a lot more polarized at low frequencies compared to the Meerkat ones. And that's also a well-known effect. And you'll notice in the top right one, for instance, one of the components is essentially turning over in frequency, that being that it increases at moderate frequencies, and then at the MWA band, it then disappears again. So just to summarize, we detected 40 millisecond pulsars. We've very precisely measured their DMs and the RMs. A lot of these pulsars that we detected are from PTAs, and a lot of them aren't reachable by LOFAR, meaning that the MWA is well positioned to actually contribute very precise measurements that LOFAR actually can't contribute for these particular pulsars. So that's an interesting niche science case that the MWA could contribute to coming up. And this census hopefully will be a useful reference catalog for SKA Low. So all of this work and more is published or has been accepted for publication in PARSA, and I've put the paper onto the archive. And also all of these detections have been put into a data release, which is published on Zenodo, which hopefully will be a trend from here on so that we can provide this reference catalog for SKA. And I'll leave it there.
A very nice summary. Thank you, Chris. Do we have any questions for Chris? I've got one. You know me, I like my ionosphere. How did you find using the global models for your ionospheric model when you were doing the RM measurements?
Yeah, so we tested a couple of different softwares to do that correction, and we also tested a few different sources of the TEC data. And essentially, we ended up narrowing down our options to essentially RM extract or spinifex, and we used the TEC data from JPL, which I know we just had a colloquium last week talking about how inaccurate that is, but for our measurements, we find that we're able to correct the ionospheric diurnal trend, so that being the trend over the course of the day, pretty accurately within the error bars that we estimate from the global models. So we're able to completely correct, flatten out that daily trend. And for us, that is enough confidence that we're pretty much happy with what we're doing here. And also in this particular census, we're not actually monitoring over time. We're mainly just doing a single snapshot of all of these pulsars. So it's not quite as important to have a super accurate ionospheric measurement for these data.
So there's no like plans of trying different models, or is it just like
yeah, so I tested out a few options, and I essentially just narrowed down the ones that best corrected for the daily trend. But yeah, that's essentially where we're at the moment.
Cool. Christian?
Thank you. Oh, very nice talk. So how did you plan the data processing in terms of how did you choose which observations to process first? What was the strategy to maximize, I guess, the chance of finding these missing pulsars? Yeah,
so yeah, that's a good question. So the pulsars are sometimes in more than one smart observation because the smart observations overlap. And in each observation, they'll obviously pass through the primary beams. They'll reach some maximum sensitivity towards that pulsar. So for each of our target pulsars, I just chose the smart observation for which the target reached the maximum beam power in our telescope. So we have the most sensitivity towards it. And then I just pulled out at least 30 minutes of data for that pulsar to process. So I tried to keep I tried to essentially beamform once on each of our targets using that particular selection strategy to make the census as uniform as possible.
Great talk. You make it sound all very matter of fact. It's pretty stunning. I'm not sure I know another example of having the entire visible sky recorded for multi-hours at the voltage level. That's a unique permanent record of the electromagnetic state of the sky. It's pretty stunning to think about and corresponds to an enormous amount of data. And I don't know, you sorted through 1.5 petabytes and you did this and did that. What lessons did you learn about the data and the archiving and how to handle the data and how to organize your workflows and how you go about your processing? Because it's a multi-petabyte bookkeeping exercise. So I don't know, maybe it's not you, maybe it's Ramesh, but it feels like there are probably some lessons you've learned about the data along the way.
Yeah, so during the processing, I guess millisecond pulsars are a fantastic way to find bugs in your pipeline. And not only a pipeline, but specifically for us, it was the beamformer. So we ended up doing quite a lot of processing that had to be redone a couple of times because we got to some certain stage and then we found some critical bug that affected all previous processing, and then we had to redo some of the analysis or some of the beamforming itself. So I guess one of my main takeaways is that we need to completely debug the software, or at least the critical bugs in the software before you go on large-scale processing. But at the same time, that's easier said than done, because for us, it was actually doing this census which helped to reveal the fact that those bugs existed in the first place. So there's a bit of a trade-off there. But yeah, millisecond pulsars are a great way to find very subtle potential problems in your processing pipeline.
Awesome. Let's thank Chris again.
Thanks.
Next, we'll hear from Chia Min about the second pass of the SMART survey.
everyone. So here I'm going to talk about the flagship project of our of the MWA Pulsar, Pulsar science. So the smart Pulsar survey itself. So so at first I'm going to talk about what the data that we have collected as part of the Smart Pulsar survey, which is also being used by Chris and others for various other science. So what we did is that we surveyed the whole southern sky at declination below plus 30 degrees. And each of our observations are 80 minutes long, and they are drift scans that pointing at a specific point at the start of the observation, and we just let it drift across the sky over 80 minutes. So our data are recorded at frequencies between 140 and 170 megahertz. So we had like a 30 megahertz bandwidth of observations. And for the purpose of the Pulsar survey itself, we had the data channelized to 10 kilohertz resolution, and with a sampling time of 0.1 millisecond. So it's very high time resolution record of the whole sky. And we did this survey using the compact configuration of the phase 2 of the MWA, which is very important for like why of choosing this configuration for the survey itself. So as of end of 2023, we had taken all 71 planned observations, including the one Ramesh mentioned just now, which covers the southern cap that it's not actually not drawn out on this plots itself. So we recorded the data with BCS. So this gives us a very large field of view for each observation, which is because the field of view is essentially the field of view of a single MWA tower. So with a large field of view, it also gives us a very fast survey speed of covering 450 degrees square of the sky per hour. So we only take about 100 hours of the MWA telescope time to complete this whole survey. So with the compact configuration, it means that our tidal array beams are relatively large. So one tidal array beam from the smart observation covers about 23 arc minutes of the sky. So we would to towel up all the observations that we had with the full sensitivity tidal array beam, we will need about 4,000 to 6,000 pointings per observation, which adds up to like somewhere close to 400,000 individual pointing throughout the whole sky if we were to search the whole sky for close to maximum sensitivity. So some background on why do we want to do this. So first of all, we have to talk about why do we want to search for more pulsars. As of the latest pulsar catalog, we had known about 5,000 pulsars, but it's still very useful to always look for new pulsars. So one thing that we are doing is an all-sky survey. So we will have like a very very constant processing way and sensitivity limit towards the whole southern sky, which will give us a very good reference point to better understand the galactic pulsar population. On the other hand, with pulsars is that there's always more interesting pulsars that's yet to be discovered. So for example, some of the stuff that I put out here, it's like pulsar triple system, which is a pulsar in a binary system with two notable orbital companion. And of course, we hope to look for more double pulsars, which is basically a double neutron star system where both of them are pulsars. And then one of the holy grail in pulsar searching that's still yet to be discovered. It's a pulsar that is in a black hole binary, hopefully with a stellar mass black hole binary. And also we hope to look for more magnetars as well. And the other thing with finding more pulsars is that we can use them as probes for, we had more targets as probes to study the interstellar medium, which is what one of the things that Ramesh hoped to do. So this can be helped by having more targets, basically more line of sights towards different parts of the sky to gives us an idea of how the interstellar medium around us is like as a whole. So the other thing is like, why do we use MWA and smart to search for pulsars? So one of it is that it will be the largest pulsar survey with an SKA precursor. So we basically would have a larger sky coverage and slightly longer dwell time than the LOFA pulsar survey that was done over the past decade. And we would have some, hopefully, skills and techniques that we learned over the course of our survey that can be applied to for SKLO. And it will be an important reference survey for SKLO and basically have a complete digital record of the low frequency, high time resolution southern sky before the start of SKLO. And it will be also complementary with other large ongoing pulsar survey in terms of sky and frequency coverage. So, previously, Ramesh's team had done first pass processing of the smart data. So with some of the students. So what was done back then was we processed 10 minutes of data for each of the observations that we get, which is about 30% of the full sensitivity of the observations. So although it's like a very small amount of data that is being processed, we're still able to find 5 new pulsars from processing just 10% of this whole sky worth of data, and also had 200 plus known pulsars that were detected, and which is in upcoming paper from Ramesh. We also use it to confirm the pulsar that found by GleamMax imaging survey, which Ramesh had touched upon it just now. So for now, we are doing our second pass processing, which will search the full 80-minute data instead of just 10 minutes of each observation. So this will give us 3 times more sensitivity than the first pass processing. And compared to the first pass processing, we also had an expanded search in terms of using a rather new algorithm to search for pulsar, which is called the fast folding algorithm. That is just basically trying to fold your time series at various trough frequencies to look for pulse signals in your data, which will be more technically much more sensitive than typical Fourier domain search that is the regular method of searching for pulsars. And we also do a larger DM range up to 500 parsecs per centimeter cube compared to like about 200 for the first pass processing. And for our data processing, because it's like a very heavy data processing, so we had to do it in like 4 different clusters. So far we are using the NT cluster from the All-Star in Swinburne. We also uses the Satonics cluster at Pawsey, as well as the dark cluster, which some support from OzSRC to help us set up our processing there. And we also had colleagues from NAOC that was able to secure time on their CNIC cluster, specifically from Meng Yao and Qiu Yang. So this is just a quick plot of like how our search pipeline would looks like. So we had to extract the raw VCS data to the various HPC cluster, and depends on whether it's legacy or MWAX data, it will be like between 40 terabytes and 80 terabytes of data that we had to transfer between two, from basically Pawsey to like whatever HPC that we are using. So from there, we had to beamform the data after calibrating it, and the beamformer that we have is capable of producing 10 simultaneous pointing for each processing, for each round of processing. So that means that we need to run like about 400 to 600 rounds of beamforming to be able to tie up one whole observation. And each of these beamforming step will produce 10 single pointing FITS files. That's like 140 gigabytes each. So it's like 1.4 terabyte each beamforming step. So we had to like cycle through the data and delete the raw data after we had searched through them. So for our search pipeline, it's just we had to do some RFI mitigation, and then we had to run a dedispersion process, which means that we had to dedisperse our data to like a large number of trial DMs, because we don't know what's the DM of our yet to be discovered pulsar. So we had to do like up to like 6,000 different DM values across our search. So that's like one very expensive part of our pipeline. And then we separate our search pipeline into 3 different methods of searching. So first is the very standard Fourier domain search of the periodic candidates. We also do the aforementioned FFA search, as well as looking for bright single pulses in the time series of our data. And then after the search themselves, we had a candidate classification to see if there are new discoveries coming out from these observations. And we'll skip this because Ramesh had talked about localization. So far we have processed about 5 full observations between our 4 HPC clusters, and then we had 4 that is ongoing on each of the 4 clusters. So with that, that's like about, I would say, 8% of the data has been gone through by our processing so far. And with that, we had actually discovered about 13 new pulsars so far, or over 8% of our data, which is a good haul from like looking at a small subset of our data. So these 13 new pulsars include 2 millisecond pulsars, as you can see on the right side of the period DM plot that we have. So compared to these unfilled star are the pulsars that we discovered on the second pass processing, which you can see that we had a larger period range and also DM range compared to the first pass compared to the pulsars that we discovered in the first pass processing. So one of the interesting one, it's this pulsar that has a 24 millisecond spin period found in a very high galactic latitude. So this pulsar has been followed up with both MWA and Meerkat, and we have detected it across a large bandwidth from large frequency range from 150 megahertz up to 2.4 gigahertz. So one thing that's interesting about it is that we found that it's in a binary orbit of more than 290 days at least, such that the sample of observation that we have with both MWA and Meerkat is unable to like model the full orbit yet. So we basically still need a lot more observations to be able to constrain the orbital parameter of this pulsar. So I'm gonna go into what are we going to do next with our survey. So one thing is that because we are processing data across multiple HPC, so we need like a central database and web page to track all our processing, as well as have all our candidates that's found by all the different HPC being collated into a single place so that we can all have it verified in a more organized manner. So this work would have some support from OSSRC as well as Data Central to hopefully get us done within the next few months. We also looking into follow-up on the smart pulsar that was discovered by the Smart Pulsar Survey. So some of the useful science that we can do is to model the rotational properties, which gives us some idea of like how the pulsars are like in terms of their characteristic age, their energetics, as well as the surface magnetic field strength of the pulsars. We also look to like model the orbital properties of the binary system, as well as hopefully looking for like any temporal variation in the pulsation properties of the pulsar. And these are like some of the things that you could find by looking at the pulsar over and over again. And to be able, and the best way for us to follow up the smart discovery is basically using the MWA telescope itself, which will require the real-time beamformer to be upped such that we could actually observe them regularly without filling up the MWA archive very quickly. And so our long-term hope is to first complete the full Southern Cap Pulsar survey by the end of the year, which covers all the observation at declination of below -70 degrees. And for our long-term plan, we had hoped to be able to complete the full survey by 2030 before the SKLO is science ready, such that we can provide them with like a reference survey telling SKLO how's the sky look like at SKLO frequency to give SKLO a better idea on like how to best optimize their strategy to search for pulsars in the era of SKLO. And that's all I have to say, and thank you for listening.
Thanks, Chairman, for the summary. Do we have any questions for Chairman? Oh, yeah, sorry, George. gosh, I didn't see you.
Thanks for that. This question is sort of for the previous presentation and for yours. It's on that last point that you've got on the slide there. That's really great. Fantastic to see. Maybe I missed this, but are you keeping track also of which pulsars, are bright enough that in the absence of scattering, you should have detected them, but you didn't detect them? Is that being recorded somehow?
So for that case, I haven't looked at like pulsars that we are supposed to detect in our observation, but I do keep track of all the pulsars that we detected in our survey. So when the whole survey is complete, we can go back and see all the pulsars that we detected, and then cross reference with the catalog and see what are the ones that we are supposed to detect but did not detect with in our smart survey. So there is like an inverse way of like doing that in a sense.
Do you have any other questions? Yes, Rob.
So I'm thinking your field of view must be a reasonable match for the Magellanic Clouds. Is a survey of the Magellanic Clouds anything you've been considering? Do you have enough sensitivity?
I haven't really thought about looking at the Magellanic Cloud, but it will be. But if we were to do that, it will be like targeted. It will be doing a targeted survey where we had to probably coherently disperse our data to get better sensitivity towards that line of sight. So that will be something that Chris Lee is actually doing at the moment, which is doing a coherent, semi-coherent dispersion survey at targeted parts of the sky. And I would say for Magellanic Clouds, we'll probably have to apply the same technique to hopefully maximize our sensitivity towards those parts of the sky.
Do you have a follow-up?
But if it's targeted, you lose the field of view advantage, which is why I thought you would be interesting, because you get your sensitivity because you're looking at all the clouds all the time.
I mean, for our case, we still had to form tidal array beams around the position of interest. So our instantaneous field of view on like a tidal array beam basis is still about 23 arc minutes. It will be the same with different techniques. So it's like we are limited by the fact that we want to do a tidal array beamforming to maximize our sensitivity.
One last quick question.
All of your talks have used the same slide, which is really nice, showing this tiled sky, which is all very neat and tidy, but you're only showing the main lobe. In a lot of those observations, there'll be some significant sensitivity and sky coverage in the side lobes. Is there any notion of at some point doing the beamforming in the side lobes as well as the main lobe? Is there any value in doing that?
I haven't really thought about that front, but probably not. I would say, at the moment, the focus is to do it on the around the main lobe. But if we could extend get our first complete survey of the main lobe done, and we had time before SKLO goes up, then we could consider doing that as well. But I would say the challenge, the other thing with doing that is that LOFA is already scanned through the whole northern sky as well, so might not be like very fruitful in terms of finding new pulsars, but might be useful for like still useful for cataloging our the whole sky.
Awesome. Wonderful. Let's thank Chairman again. All right, our next presentation is from Chu Yang, who is online.
Chu Yang, do you want to try sharing your screen?
Okay. Can you see the slides?
Yeah, it looks great. Thank you.
Okay.
I'll come on and give you a 5 and 2 minute warning through the microphone.
Okay. Hi everyone, I'm Chu Yang Fu, a PhD student from NOC. The topic of my work today is improving Pulsar search efficiency in next generation Pulsar surveys with artificial intelligence. This work uses AI to boost the speed of Pulsar search pipeline. The Pulsar search is the process of using telescopes to detect periodic signals radiated by pulsars. The challenge is that pulse signals are usually very faint. To address this, we first correct for the frequency-dependent time delays caused by dispersion, then for the long observations data based on their periods. The period is obtained with the fast Fourier transform, which transform the signal from the time domain to the frequency domain, resulting in peaks at the fundamental frequency and its harmonic corresponding to the period to the potential period. When performing a blind search for an unknown pulsar, we aim to determine its two unknown parameters, the dispersion measure and the period. After dispersing the data over a range of DM values and applying a Fourier transform, we obtain a large set of candidate DM period combinations. Each combination must be folded over the data, which leads to challenge. A large number of candidates are generated, and folding on the data is time-consuming. As an example, for a 30-minute observation data with FAST, we divided the data into 10, 20, 30-minute segments and perform blind search over 100 adjacent DM values. From the proportion of time spent at each step, we find that as the observation time increases, the number of DM period combinations grows, and the folding step takes an increasingly larger fraction of the total processor's time. Due to the MWA's large field of view, it can cover the observable sky in under 100 hours, using 80 minutes per observation. For its observation, 6,000 to 8,000 beams need to be beamformed, and each pointing generates 138 GB of data. The massive data volume presents a significant computational challenge during survey processing. As observation time increases, the folding step increasingly dominates the processing time. So we explored a strategy for the search processing based on FFT search. After generating candidate DM period combinations, we need to fold in the full data according to its DM and period, producing pulsar candidates like those shown in the upper right figure. Folding on the full data provides time and frequency information, but is time consuming, especially when we need to try every combination. Therefore, we built a model, and the AI model is used to shift the snapshot pulsar candidates, which are quickly folded from de-dispersed time-series data instead of the filter bank or PSR phase data. So the AI model selects only a small fraction of candidates that need to be folded using the full data for final inspection. And we use a network to extract the profile and the time phase feature for each candidate and identify whether it's a pulsar. This helps us filter out candidates that are unlikely to be pulsars based on time domain features. And because candidates with different periods requires different numbers of beams for folding, so the size of the input data are not the same. However, neural network require inputs of the same size. Previous models therefore resize all inputs to a uniform size, but this can reduce classification performance. And we can build a wider or deeper networks to increase the number of parameters and improve the model's performance. So we resize the input features to 3 different sizes and feed them into separate branches of the network. This effectively increases the network width and enhances its ability to capture features at different resolutions. We also input the two-dimensional features into a denoising model. The model effectively removes noise and highlights the features. So our pre-processing workflow first resets the input data to 3 different sizes, then denoise the two-dimensional time phase feature to highlight the feature, and finally feed them into the classification model. And the model architecture is shown in the figure. One-dimensional features are extracted using a simplified one-dimensional ArcGIS-Night, while two-dimensional features are processed with convolutional neural networks enhanced by attention mechanisms. The attention mechanisms allows the model to focus on the most relevant regions. After extracting the post features, the features are fused and passed through a linear classifier and output the probability that the candidate is a real poster. We also provide a fine-tuning interface for the model. The fine-tuning will keep the model feature extraction ability learned from a large data set while adapting to the new telescope's data distribution with a small data size. We also developed a script to generate a simulated pulsar, optimizing the training site or improving model performance. This allows us to inject pulsars into background data from newly built telescopes. Next, I will introduce the model's performance in terms of classification and further step acceleration. As our work is supervised learning tasks, so the model learns to identify whether a sample is a real pulsar from labeled data. So we collected candidates from the FAST, PAX, and Arecibo telescopes using 3/4 of the data for training. By minimizing the loss function, the model learns to identify pulsars. The remaining 1/4 of the data is used to evaluate the trade model using the 4 matrix shown on the right, with high values indicating better performance. The results show excellent performance across all 3 telescopes. We also compared our model with the PIX model developed by Wei Zhu. PIX used a 2-layer ensemble model. In the first layer, 8 classifiers scoring 4 features, and in the second layer, a logistic regression combines these 8 scores. For comparison, we averaged the ANN and the CNN scores from PIX that focus on time domain features, and compare them with our model, which is specially designed for time domain features. First, we compared the two models using a data set from a GBNCC survey. PIX used all 4 features, while our model, MOTI, used only time domain features. MOTI showed high performance in identifying both fundamental and harmonic pulsar candidates, using either the standard threshold of 0.5 or a lower threshold or 0.3, and all pulsars can be detected. But more known pulsars are classified as positives. This is because without frequency information, narrowband and 0 DM RFI cannot be identified, leading to more false positives. However, this problem has little impact for smart survey. We tested both models on 10,000 samples using only time domain features. Thanks to MWA's excellent radio environment, our model MOTI achieves high performance for both pulsar and non-pulsar samples. Additionally, we also fine-tuned our trade model for smart survey. Using our simulation program, we generated 300 pulsar samples based on MWA observational template data, and add another 200 positive samples from the smart survey. After fine-tuning, we can see the model's performance improved further. After get a model, We further evaluated its performance on accelerating the folding step in Pulsars. The n sub 0 denotes the number of candidates generated by Bristol, and the n sub 1 means the number of candidates require folding after AI model filtering. Because folding the dispersed time series data is much faster than folding the full data, so the acceleration factor for the folding step can be approximated by the ratio of the number of candidates after model filtering to the total number of the DM period combination generated by the post search. We analyzed the acceleration using fast observation of the globular cluster M5 within a restricted parameter space containing 7 known pulsars. We defined the search parameters based on their DM range. The search pipeline generates 1,000 candidates, including 5 detectable pulsars. The remaining 2 pulsars cannot be detected in this observation. With a threshold of 0.5, our model reduced the list to 100 candidates while retaining all 5 detectable pulsars, achieving a tenfold acceleration of the folding state. We also evaluated acceleration in a large-scale parameter space using the SMART survey. In G13 observation, 43 known pulsars are detectable using search parameters approximating pulsar serving settings. We processed the beam-formed data of these 43 pulsars, generated 26,000 potential DM period combinations. Applying a 0.5 threshold reduced the list to 400 candidates for data folding, and recovering all 43 pulsars. They showed that in large-scale parameter space, similar to the SMART survey, the folding step can be speed up by a factor of 60. Building on this, we performed a blind search over 960 pointings in the survey, producing 570,000 pulsar candidates. Applying a 0.5 threshold reduced this to 6,000 candidates, showing that extending to the full SMART survey, it will further increase the acceleration performance. Due to the wide field view of MWA, long observation time are adopted for pulsar surveys. As the observation time for single point is prolonged, the resulting raw data size increases correspondingly. Our developed method will effectively accelerate pulsar search if folding dominates computational time, and the main innovation are that pre-shifting stem sort candidates in time domain feature in speeds up the folding step by a factor of 60 in a similar to a SMART survey parameter space. And our simulation program enable fine-tuning for newly constructed telescopes to improve performance. And we decided a robust model that achieves high performance across different telescopes. And the methodology establishes a reliable pathway for deploying an AI model in pulsar surveys of next generation telescopes, such as the SKA. That's all for my presentation. Thank you all. This work has been submitted to MNRIs. Thank you.
Chuyang, for the very interesting presentation. Do we have any questions in the room? I'm also looking online if there's online questions. Christian?
Thank you for the talk. It was incredibly interesting. Can you hear me, first of all? Yeah?
Okay, I can hear you.
Yeah. Could you go to the slide of the performance results, or the recall and precision slide? Yeah, the results one, you passed it one. So the one with the table with accuracy, recall, the scoring.
Okay.
Yeah, that one. So is that scoring? Can you confirm it's on the validation test set?
Yeah.
So that's great results. But the architecture, is for what I can understand, do you think it's quite complex for that data set size? I mean, did you try simpler models before going to that one, or what was your process for deciding that architecture? Because it may be overfitting, or
Uh, 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 I, 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 I think the poster feature is simple. So I decide the model. I use the simplified RESNet and convolutional two-dimensional 那个convolutional. So I think the model parameter is not big. When we enhance the parameter, the program running a long time, but its performance is not enhanced a lot.
another point is, did you think of studying the weights, the features is actually learning within the model as a way to represent information within the data set? So similar.
Because we want to build a robust model can get high performance in different telescopes. So we collected total five telescopes poster candidates.
Okay, thank you.
Do we have any other questions? Oh yeah, this microphone's a lot better than the other one. I have one quick question. Do you think you could use similar models for other transients, not just pulsars, but maybe like the long period transients we heard about yesterday?
If you want to find the long period transient, maybe you can maybe you need to decide the special model, adopt the data sets come from the survey.
Cool. Thank you very much. All right, wonderful. Well, let's thank Chu Young again for their presentation. All right, we have our final speaker of the session, Piyush, talking about how we're going to be speeding up our pulsar searching.
Thank you for the introduction, and hi everyone. I'll be talking about speeding up the Pulsar search pipeline. So I'll begin just by telling a little bit about myself. I'm an HPC application developer at CTAS EPFL, and I've been working on this project in collaboration with Ramesh Bhatt and his team here at the Curtin University. Okay, so what is a pulsar? I guess most of you know a bit about this already, since there have been a few presentations, but it's a rotating neutron star, as you see here. It has a very strong magnetic field, and it's emitting electromagnetic radiation from its poles. And when it crosses the line of sight, it creates a peak in the signal, as you see there down on the bottom. And then the question is, how do you detect these pulsars? So when you think about that, these objects there in outer space, by the time this periodic pulse reaches Earth, it's already distorted. And there's two major sources of distortion that I'll be focusing on in this presentation. The first one is the distortion coming from the motion of the pulsar. So when it's orbiting some other object, as shown by Christopher Lee in his presentation, the phase gets nonlinear, which is a distortion. And the other one is the interstellar medium through which the signal passes. And by the time it reaches that, it's dispersed and there's some noise added on top of it. So from my point of view, which is my background, which is computational science, it's just about undoing these distortions to the signal, and then you fold the signal, as you see here on the bottom, to recover the pulse in the end. And as mentioned before, these distortions, they're caused by these parameters, which are not known to us. We don't really know how it's orbiting something in outer space or what's in between us and the pulsar. And the way then this detection or this undoing of distortion happens is that we just try undoing these for a bunch of parameters. We just do hidden trial, basically, and try to find the right one. And the way it's done currently in the SMART Pulsar survey is using the software Presto, which is written in CPU only, and only has some very basic parallelization using OpenMP, which uses multiple threads, or either using MPI, which uses different nodes. And the problem with using this software is shown here on the slide. There's this large amount of data, approximately 4 petabytes. And in the first SMART survey paper, they estimated the time they would take to finish the entire search is around 23 years, which is not very good. So, and that's where I come in. I try to do a GPU acceleration of the search algorithm, which inherently are quite parallelizable and take up about 90% of the time. So this figure here, I'm talking about this 90%. It's, of course, not including the folding, which was talked about also in the previous talk. So again, in this presentation, I'll just be focusing on de-dispersion and acceleration or jerk search. You might wonder what's the obsession with GPUs? And I'll try to just show a little bit here and show the difference between CPU and GPUs. So on a GPU, as you see on the right, you have many small, many slow cores, and it's the architecture is designed to handle parallel computation with a very high throughput compared to a CPU on the left, which is designed mainly for sequential computation. And this fits perfectly with what we want to do in our search pipeline, which is do the same computation over and over again for a bunch of different parameters. So let's talk about de-dispersion. So as you also saw this figure in the previous slide. Okay. So when you receive the signal from these pulsars in outer space, the signal across different frequency values gets a different delay, which is exactly what dispersion is. And you can see it here. On the y-axis, it's the frequency of the channel. On the x-axis, it's the phase. And you see, as you move in frequency, the pulse sort of moves. So there's a delay that comes in because of the interstellar medium. And in de-dispersion, you're essentially trying to fix this delay. And there's two main routes that you can take. You can either do it in time. So you have a model for how this delay looks like. You compute the delays and just shift the channels and sum the time series to get a de-dispersed time series. This is the time domain version of the algorithm. And you can do the same thing in frequency domain. So instead of physically shifting the channels, you just do a channel-wise FFT and multiply a complex phase factor, which is here, which essentially does the shifting in the Fourier domain. So if you know Fourier transform of a shifted series is just the original transform times this shift factor. And then, yeah, in the end, you do a sum of these coefficients and you recover the d-dispersed time series. And in the smart survey for shallow processing, they wanted to use about 2,000 DM values, but for a full processing, they want to use about 10,000 trial DM values. I mentioned these two algorithms, the time and frequency domain, and there's a difference. And you see this difference when you think about the whole pipeline and look at d-dispersion in context of that. In the next step of the pipeline, you inevitably end up having to do an FFT of this d-dispersed time series. So if you follow the time domain route, of course, you would do as many DMs as there are trial DM values, so number of DM FFTs. But you can do something clever in the frequency domain approach, is you can skip doing the inverse transform here, just do a sum, and you actually directly get the FFT of the d-dispersed time series. And with this approach, you can see that you only end up doing number of channel FFTs compared to number of DM FFTs. And also for the Fourier domain algorithm, it's more suitable for use on a GPU because memory accesses here are more regular because you're not dealing with arrays which are shifted in some random fashion. Coming to the implementation, so here I was fortunate to come across this implementation I mentioned, which I used as a starting point for what I did. I made some changes to this implementation to make it usable for this smart search case, where we deal with things like fixed inputs or float data types. And there were some critical issues in the library, some conceptual issues like incorrect frequencies and the computation of shifts. But fixing these and making it Presto-like so that it could be easily integrated into the existing pipeline, and also doing a HIP implementation. So HIP, for those of you who don't know, it's just an API to develop codes for both NVIDIA and AMD GPUs. So of course, this could be used on Photonics then. There's a few more things I want to do here, which is implementing downsampling and barycentering, things like that, which make it a bit more usable for this smart test case, and eventually moving to an MPI plus GPU implementation so that we can process the whole observation at once. But with these changes, I also did some timing results. You see them here. So it's for 3,072 channels, 2 to 8 million points, no subbands and no barycentering. I did the GPU runs on Kuma. This is the cluster we have at EPFL. It has an H100 GPU. And just for a comparison, I also checked out some recent GPU implementations of Presto, which is Presto GPU and this Presto ZL. And to compare with Presto, this original legacy software on CPU, I ran it on JED, again, a cluster at EPFL, using MPI on 21 nodes, 10 cores per node. And these are the results here. On the left, you see a comparison for just 2 million points, Presto GPU, Presto ZL, and DDIS is the implementation I have. And you can see as you go to a higher number of DM values, it's far better compared to these other GPU implementations. And the other ones actually couldn't go beyond 900 DMs, but I was able to push this library to even 10,000 DMs. So on the plot on the right, it's just DDISP at different lengths of the input time series, so 2, 4, 6, and 8 million points. And yeah, on the x-axis, it's the number of DMs. And you can see for 5,000 DMs and 8 million points, you're around 2 minutes to do the d-dispersion, which is amazing. And you might notice that Presto is missing from these plots, and here's the reason why. For 1,000 DMs, it took about 2,900 seconds, and 4,000 DMs, it's 12,000 seconds, so 3.5 hours. So no point in putting it on this slide. So I also tried to run, this is something recent, I actually did this yesterday. I tried to run the software on different pieces of hardware just to see what it gives, and it's quite interesting. So I ran it on Photonics, on Doug. These are the two platforms which they plan to use, and Kuma, and got these interesting results for different DM values. And so it basically reveals that the processing times are rather similar. It's just I/O where things differ on these different platforms. I'm running out of time, so I'll maybe speed up a little bit. Just to show you it's not just accelerating numbers, but you can actually get a detection. So thanks to Christopher, I was able to get this image where on the left, you can see a detection of a non-accelerating pulsar using DDISP. And on the right, it's from Presto, this legacy software. So now I'll come to acceleration search. So here we try to undo the nonlinear phase, which is arising from the acceleration of the pulsar. And the way you do it is you just do a matched filtering with templates, which look like this. So cosine with different parameters for R, which is the frequency dot, which is Z, and the double dot, which is W. And yeah, for a full processing, you want about 15,000 of these templates. And in the end, you just match them with your input. And for example, with W equals 0, you would expect to see a plot like this, a 2D plot, where you see a peak and you say, bingo, that's the pulsar. And again, this is a very parallelizable algorithm because you just end up doing the same thing for a bunch of different parameters. And here coming to the implementation. So this is something I started working on recently, only a couple of months ago. And again, instead of reinventing the wheel, I found this very nice library, PrestoZL, which had a nice implementation. And I've only worked on it for a short period of time. I did some optimizations concerning the kernel generation and improving little things like memory transfers from device to host and reusing memory allocations and so on, and some very slight improvements to the CUDA kernels. There's still some work to do, some ideas I have in mind about optimizing this library, and eventually moving to a HIP implementation, and then to an MPI plus GPU implementation. So I'll show some preliminary results here with this library. So the results you see here are for 2 million points with 32 harmonics summed, interbedding enabled, and just some sigma value that shows it to be 2.0. Again, so here I did the GPU runs on the GH200 GPU, so it's a Grace Hopper node where I did this. I compared PrestoZL, PrestoZL tests. It's an unimaginative name I chose for the library I have, but okay. And Presto GPU, this another recent GPU implementation. And to compare with Presto here, I did the CPU runs on Jet again on a single node with just 8 cores. And you see here the results. Yeah, again, GPU implementations are much better compared to Presto. And I'm able to get some slight improvements in PrestoZL. So the red line you see is the best implementation I have currently, which is what I worked on recently. So that brings me to the end of my talk. So to conclude, I worked on GPU acceleration of the D-dispersion and the acceleration search algorithm. And compared to Presto, it's just much superior in performance. And for a high number of search parameters, I can easily get up to 100x in performance. And it's also better compared to other GPU implementations, especially for D-dispersion. There's some further optimizations I plan to do, and eventually move to also AMD GPUs for Cetonics, and in the end, an MPI plus GPU implementation. And for those of you who are interested, you can find the codes here. And thank you very much for your attention.
Thank you, Piyush, for the wonderful talk. Do we have any questions for Piyush?
Marcin Sokołowski. Great work and very cool results. I was just wondering, could you go to slide 15, I think, where you had comparison of this pulsar detection? So, oh no, next one, please. Oh, so that one. So the left one is your result and the right one is the standard Presto. Exactly. Should we be worried a bit that the pulse profile is different between the two, or is it like on different data? I mean, I would expect that.
It's the same thing. So in the end, you end up doing computations in floating precision, and of course, the FFT route has different amount of computation. So the errors sort of pile up, and you see tiny differences. It's just because of finite precision.
Okay, so these are the accumulation of errors when you do floating point operations on GPU, which we saw in our imager as well. But here, these differences look a bit large to my eye, at least. Okay, maybe that explains this. Thanks.
Christian?
Yeah, I guess I also want to reiterate what Marcin said. I think I also tend to attribute to floating point errors a lot of things that then we find out it's some other things, but so just keep an eye on that. But great results. And what I was wondering, what do you think the other GPU implementation missed and that didn't do to get that same results you did? So what did you add to them?
I think the other GPU implementations are really sort of a naive translation of Presto into GPU and not really thinking about the algorithm and how you can take advantage of things.
Yeah, I think that the thing you did that noticing that you could skip a step and just move to the knowing the way the output was going to be used next, that was a great point. Cool.
Any other questions? Yes, Stephen.
Yeah, just the next one with the comparison between the run times, I guess.
This one?
Yeah. You said the improvement with the EPFL cluster is clearly the I/O. Yes. Is that a meaningful difference, or is that do you only care about the processing time, or is the I/O something that's inherently different between the different machines? Can it be fixed for Photonics and Doug, or is there something special about the EPFL machine that gives that difference?
I mean, this was tried on the Scratch file system on EPFL, if I remember correctly. It's GPFS. Here it's Luster. It also depends on the usage of the file system at any given time. You could get very high numbers even on Photonics. And something that could work on Photonics is the use of the local NVMEs, which I was talking to Ramesh about today. So you can have ideas like, because the I/O time is sort of similar to the processing time, you can, in the background, try and load the next observation while the processing is going on. I'm not sure about Doug if they have local NVMEs, but at least on Photonics, I know that they have it.
Right. Do we have one final question for Piyush? All right. I mean, let's thank Piyush and all the other speakers in the session again. And I'll hand back to the organizing committee to close off for the day.